Welcome to the first lecture of Ec2723, Chapter 1, Choice Under Uncertainty, and this is Module 1, which is the first part of the chapter. In this module, I'm going to briefly review basics of utility theory, introduce Jensen's inequality, relate that to the measurement of risk aversion, describe some results on comparing risk aversion across investors. I'll briefly mention decreasing absolute risk aversion and the plausibility of that assumption. And finally, I'll introduce the Arrow-Pratt approach for analyzing risk premia for small risks. So going back to the basics of utility theory, as I'm sure you already know, there is an important contrast in utility theory between ordinal utility and cardinal utility. So ordinal utility is invariant to monotonic positive transformations, so that we can take any utility function, apply any strictly increasing function to it, which may be nonlinear, and it will be an equivalent representation of preferences. This is, of course, what we do whenever we draw indifference curves in a basic microeconomics diagram. There's no labels on those indifference curves. The only thing we can say is that something is preferred to something else, but we don't have any units for comparison. Now, cardinal utility, on the other hand, is invariant only to positive affine, or otherwise stated linear transformations, so that if we have a cardinal utility function, we can always add a constant, we can always multiply it by some positive number, and that will encode the same choices. So with cardinal utility, we have no natural units. There's no such thing as a util in which we can measure utility, and this is why we have these arbitrary constants A and B. Now, in finance, we rely heavily on von Neumann-Morgenstern expected utility theory, which says, as you know, that choice over lotteries that satisfies certain axioms implies that investors behave as if they're maximizing the expected value of a cardinal utility function, which is defined over outcomes. And there's a sketch of the argument in Chapter 1 of the book. I'm just going to assume that you know this material. Now, in finance, we tend to work with particularly simple versions of von Neumann-Morgenstern utility. In general, one can write utility as a function of consumption of multiple goods at multiple dates in multiple states of nature. And that would be the most general micro description of utility. When we're looking at different states of nature, it would be an ordinal utility function. If we then simplify to a model in which we evaluate utility over multiple goods and dates while taking the expectation over states, that's cardinal utility. But that's still complicated because we have multiple goods. Very often in finance, we simplify to one good. We're going to ignore choices over goods and work with a single good. Then we have multiple dates, but only a single good. Finally, we might assume time-separable utility, in which case we can add up over dates using a time discount factor delta, and then we'll have the familiar time-separable utility function, which is often used in macroeconomics. And then finally, in the first part of this course, we're going to be considering single-date models, where we just have utility of consumption tomorrow, which is U of C1, C1 referring to consumption at date 1. And if there's only one period, all wealth tomorrow is consumed, so this is going to be equivalent to defining utility over wealth, U of W1. And that's the class of very simple models that we're going to begin working with. Now I want to introduce Jensen's inequality. And frankly, this is going to play an extremely important role in this course. It would be a little bit of a caricature, but not totally wrong, to describe asset pricing as the economics of Jensen's inequality. We're going to apply this result again and again in the course, and it's really foundational. So what is Jensen's inequality? We're going to consider a random variable, z tilde. The tilde here denotes a random variable, and a function f. We're first going to define what it means to say that the function f is concave. This should be pretty familiar. F is concave if and only if for all lambda between 0 and 1 and values a and b, which are arguments of the utility function, the weighted average, using lambda and 1 minus lambda as the weights, the weighted average of the function is less than or equal to the function of the weighted average. So very familiar textbook diagram of this here shows a concave function. We have arguments a and b, and then we can take lambda a plus 1 minus lambda b. That's a convex combination of the arguments a and b. That's somewhere in the middle. And the function is concave if the weighted average of fa and fb found by following this straight line is less than or equal to the function evaluated at the point lambda a plus 1 minus lambda b, which is this point. So it is the downward curvature of this upward sloping function that in this case reveals the concavity. Now, if f is twice differentiable, then concavity implies that the second derivative of the function is negative. That is, of course, is what gives us this curvature in this diagram, is a negative or weakly negative, non-positive second derivative. All right, that's just the definition of concavity. What is Jensen's inequality? Jensen's inequality is the statement that if we consider all possible random variables z tilde, then the statement that the expectation of the function is less than the function of the expectation. That's true for all possible z tilde if and only if f is concave. Okay, so why do we care about Jensen's inequality? Let's start to use it. We will use it by thinking about the definition of risk aversion. So on this slide, I've rewritten the definition of Jensen's inequality at the top of the slide. And now let's define the concept of risk aversion. An agent is said to be risk averse if she weakly dislikes, that is, fails to prefer, any zero mean risk at any level of wealth. So for all initial wealth levels W0, and for all arbitrary risk distributions x tilde that have a mean of 0, E of x tilde is 0, we require that the expected utility of wealth plus the risk is less than or equal to the utility, the known utility of wealth without the risk. This is what it means to say that somebody is risk averse. They're going to turn down any zero mean risk, and that's true at all initial levels of wealth. Now, of course, this equation, the first equation on the slide, is equivalent to this one written below, where we replace W0 plus x tilde with z tilde, a new random variable, just defined to be initial wealth plus x tilde. So we're saying, for risk aversion, we're saying that the expected utility of z tilde is less than or equal to the utility of the expectation of z tilde for all possible z tilde. And now if you look back up to the top of the slide, you look at the definition of Jensen's inequality, you can see that risk aversion is equivalent to concavity of the utility function. Now let's talk quantitatively about how we might measure risk aversion. So far we just had a qualitative definition. You're either risk averse or you're not. But can we measure how risk averse somebody is? Well, since risk aversion is defined by concavity, and for a twice differentiable utility function, concavity is captured by the second derivative, it's natural to measure risk aversion using that second derivative. But of course, we're going to have to scale it appropriately to avoid any dependence on the units of measurement for utility, because as we said at the beginning, cardinal utility is invariant to positive affine transformations. So there are no natural units. So how are we going to scale? We're going to scale by the first derivative. That way, if you multiply the utility function by any positive coefficient, it won't change the measure of risk aversion. So absolute risk aversion then is defined as minus the second derivative divided by the first derivative. We have the minus sign, the negative of the second derivative, because the second derivative is negative and our measure of risk aversion is positive. Now, in general, absolute risk aversion is a function of wealth. It'll depend on how much wealth you have initially, and that's why we write it as a function A of W0. Now we're going to talk about how we might compare risk aversion for two agents, two people. So let's define the people by their preferences. They have preferences U1 and U2. And we would say that person 1 with utility U1 is more risk averse than person 2 with utility U2 if U1 dislikes all lotteries that U2 dislikes, regardless of the common initial wealth level. So we're going to make an apples-to-apples comparison by giving each person the same level of wealth, but we want the comparison to come out the same regardless of what common initial level of wealth we consider. Okay, so how are we going to analyze this problem of comparing risk aversion? We're going to do it by defining a new function phi of x, which is the u of 1 applied to the inverse of u of 2. Now, what does this function do? So the first thing we can do is we can write u1 of z is phi of u2 of z. That's true by the definition of phi. It just says that what phi does is it turns u2 into u1. Now, once we have this equation here, we can differentiate it. We can differentiate both sides with respect to the argument z. And on the left, of course, we just get u prime 1 of z, the first derivative of u1 of z with respect to z. And on the right-hand side, we apply the chain rule of differentiation, and we get phi prime of u2 of z times u2 prime of z. So then we learn that phi prime is u1 prime over u2 prime. These marginal utilities are both positive, so we learn that phi prime is also positive. Okay, now take this equation and differentiate it again. This trick of repeatedly differentiating is going to be commonly used in our course, as you'll see. We're going to differentiate again. On the left, we get the second derivative of u1 double prime of z. And we apply the chain rule again on the right. We get all of this stuff, phi prime u2 double prime plus phi double prime u2 prime squared. So if we rearrange that, phi double prime is u1 double prime minus phi prime u2 double prime divided by u2 prime squared. And notice we've got a ratio of second derivative to first derivative in here. Okay, so we can write this as u1 prime over u2 prime squared times a2 minus a1, the difference between the absolute risk aversion coefficients of person 2 and person 1. All right, now we can start to use those results. So we're comparing the risk aversion of two people, U2 and U1. So let's consider a risk X that person 2 dislikes. So that's going to be a risk such that the expected utility of wealth plus the risk for person 2 is less than or equal to the utility of initial wealth by itself for that same person. So this is the statement that at any level of initial wealth, person 2 dislikes the risk. Now, what we want is to say that person 1 is also going to dislike the risk. In other words, that expected utility for person 1 of wealth plus the risk is less than or equal to the utility for person 1 of the initial wealth over here on the right. We want that to be true for all x. Now, what's that going to require? Well, it's going to require that phi is concave, or equivalently that the second derivative of phi is non-positive. So let's take a look in here. The expected utility of w plus x for person 1 is the expectation of phi of u2 of w0 plus x. That's true from the definition of phi. And we want that to be less than or equal to phi of e of u2. Which in turn is less than phi of u2. This is going to require the concavity of phi, and this just requires the risk aversion of person 2, the fact that person 2 dislikes the risk. And then, of course, phi of U2 of W0 is U1 of W0. So to make this go through this chain of inequalities, we have to have concave phi. That's what gets us from this step to this one. And if phi is concave or the second derivative is non-positive, what does that require? We'll go back one slide. We know that the second derivative is proportional to the difference in risk aversions. So we must have that A1, absolute risk aversion for person 1, is greater than absolute risk aversion for person 2. All right, so what we've done now is we've shown that if one person is more risk averse than another, they have to have higher absolute risk aversion at any initial level of wealth. Now we can also come at this a different way. Let's define the risk premium, pi, which is going to depend on initial wealth, the utility function, and the risk. We're going to define the risk premium as the amount a person is willing to pay to avoid a pure zero mean risk. So we're going to only consider x here with zero mean. So it's the solution then to the equation expected utility of wealth with the risk is the known utility of wealth minus the premium that you're willing to pay to get rid of the risk. So if we now define z as initial wealth minus risk premium and y tilde as risk premium plus x tilde, you can rewrite this as expected utility of z plus y is utility of z. Then we define the risk premium for agent 2 accordingly, define z2 and y tilde 2 accordingly. If person 1 is more risk averse than person 2, then the expected utility of z2 plus y2 for person 1 is going to be less than or equal to the utility of z2 for person 1. That's what it means to say that person 1 is more risk averse, is that they dislike any risk that person 2 dislikes, and in this particular case they weakly dislike any risk that person 2 is indifferent to. But if we have this statement, this is equivalent to saying that the risk premium for person 1 is greater than or equal to the risk premium for person 2. Now, another way we can come at this is to think about certainty equivalence. So the risk premium is what you'll pay to get rid of a zero mean risk. The certainty equivalent is the amount that makes you indifferent to a non-zero mean risk. So let's define the mean of the risk as mu. So we're being offered a risk that pays mu plus x tilde, where x tilde is the zero mean part. And the certainty equivalent, CE, satisfies expected utility of wealth plus the total risk mu plus x tilde is the same as the known utility of wealth plus the certainty equivalent. Well, you can see the certainty equivalent is really just a minor variation on the risk premium. It is in fact, the certainty equivalent is in fact the mean of the risk minus the risk premium that you would pay to get rid of it, starting from W0 plus mu. And so the previous arguments imply that if person 1 is more risk averse than person 2, then the certainty equivalent of any risk is lower for person 1 than for person 2. Let's put all of this together. What we've learned is that the following statements are all equivalent. Person 1 is more risk averse than person 2. Person 1 has a utility function that is a concave transformation of the utility of person 2. Person 1 has higher absolute risk aversion than person 2 at common levels of wealth for any initial level of wealth. The risk premium for person 1 is higher than for person 2. Again, the risk premium will depend on the initial level of wealth, but we're comparing them at the same initial wealth levels. And finally, the certainty equivalent for person 1 is less than or equal to the certainty equivalent for person 2. All right, so that completes the analysis of the comparison of risk aversion. Let's just talk for a moment about how risk aversion may vary with the level of wealth. I will simply state on this slide, without proving it, that a risk premium that decreases in the initial level of wealth for any given risk is equivalent to saying that absolute risk aversion decreases in the initial level of wealth. One can show, this goes back to Miles Kimball in 1990, one can show that these conditions are equivalent to saying that the negative first derivative of utility is a concave transformation of the first derivative, so that the negative ratio of third to second derivative is always bigger than the negative ratio of second to first derivative. This third to second derivative ratio is called absolute prudence by Kimball, and so decreasing absolute risk aversion says that absolute prudence exceeds absolute risk aversion everywhere. This comes into the theory of precautionary saving because you need a non-zero third derivative of the utility function, non-zero prudence, to get precautionary saving in your model. Now, I'll just say here that decreasing absolute risk aversion, or DARA, D-A-R-A, DARA, seems intuitively appealing. Why? Because we might think that a very wealthy person would pay a smaller amount to get rid of an absolute dollar risk than a poor person would. A minor risk will be trivial to Jeff Bezos. That same minor risk might be important to you, so you would pay more to get rid of it. So for this reason, many people have the intuition that decreasing absolute risk aversion is a desirable property of a utility function. Certainly, I think we should be uncomfortable with increasing absolute risk aversion, which would imply that Jeff Bezos would pay more to get rid of a given dollar risk than you would. And this is one objection to quadratic utility, which does have increasing absolute risk aversion. Now, finally, in this first module, first recorded module, I want to talk about the Arrow-Pratt approach for solving for the risk premium for a small risk. So, in general, the risk premium is only defined implicitly. So, it is the solution to some equation, but we don't, in general, know how to solve that equation explicitly. But what the Arrow-Pratt approach does is that it considers a small risk. So we're going to take an arbitrary risk x tilde, we're going to multiply it by k, some scale factor, we're going to let k get small, and then consider what happens. So y tilde is k times x tilde, and we're going to think about small k. Now let's write the risk premium as a function of k, g of k. G of k is just the risk premium that corresponds to the initial level of wealth, the utility function, and the risk k x tilde. And it's got to satisfy this equation by the definition of a risk premium. The expected utility of wealth plus the scaled risk is the utility of wealth minus the risk premium you pay to get rid of it. Now, first point, if k is 0, then there is no risk and you wouldn't pay anything to get rid of it. So g of 0 is 0. But now we're going to use our repeated differentiation trick. We're going to differentiate this equation here with respect to k, and we'll, on the left, we'll get the mean of the product of x tilde and marginal utility, and on the right-hand side we'll get minus g prime of k times marginal utility of wealth minus g of k. Now, let's consider what happens. This implicitly defines the first derivative, but let's consider what happens at k equals 0. The first derivative at k equals 0 is just going to be 0. Why? Because if k is 0, u prime is a constant, it's known, and the mean of x is 0, so the whole left-hand side is 0. This marginal utility here is positive, so for the equation to hold, g prime of 0 must be 0. Okay, that's not very interesting yet, but let's hang on a minute. Let's differentiate it again. On the next slide, we're going to differentiate with respect to k a second time, and we get this long equation. We're just applying chain rule, and again, let's evaluate it at 0, at k equals 0, and figure out what it tells us about the second derivative at 0. G double prime of 0, well, if we rearrange this equation, and again, remember we're setting k equals 0, we're going to get that the second derivative of G is minus u double prime, second derivative of utility, divided by first derivative of utility, times the mean of x squared. So it's this stuff on the left, and then we get this marginal utility on the right. But what is this? This is just absolute risk aversion, A of W0, times the mean of the square of the risk. Now, how do we use this? Well, we're going to take a Taylor approximation of G of k, the risk premium we're interested in solving for, around the point k equals 0. And this is going to be a good approximation for a small risk, for small k. So G of k is approximately G of 0 plus k G prime of 0 plus 1/2 k squared G double prime of 0. The first two terms are just 0, so they drop out. So we're just going to get the risk premium pi, or equivalently G of k, is 1/2 absolute risk aversion times k squared times the mean of x squared. But of course, k squared times the mean of x squared is just the mean of y squared, the mean of the scaled risk that we face. So we learn that the risk premium is proportional to the square of the risk. That's very important. It's known as second order risk aversion, and it's a property of any differentiable utility function, twice differentiable utility function. It implies that people are approximately risk neutral with respect to small risks, because as the risk shrinks, the risk premium goes to 0 with the variance of the risk, with the square of the scale of the risk. Okay, and risk aversion, the risk premium is also proportional to absolute risk aversion. So here we can see that absolute risk aversion is a very useful quantitative measure of the risk premium, the observable quantity that people are willing to pay to get rid of a risk. We can, of course, apply this to the study of the certainty equivalent. We find the certainty equivalent is k mu, the mean of the risk, minus that risk premium. And what this tells us is that a positive mean, mu, has a dominant effect for small risks, because as k gets small, k gets large relative to k squared, and so the certainty equivalent is going to be positive as k gets small. Finally, last slide for this module, we can apply all of this to relative risks, multiplicative risks. Let's consider a risk which multiplies your initial wealth. So define W tilde, wealth tomorrow, as wealth today times 1 plus kx. So this is the multiplicative risk that we take, and kx is the same as y. We're going to define pi hat to be the share of wealth that you would pay to avoid this risk. So that's the risk premium you would pay to avoid the absolute risk W0 kx tilde. And then we scale that by wealth. So it's the risk premium divided by wealth. It's the share of wealth you would pay to get rid of the risk. Well, a little algebra using the previous equation says that pi hat, the relative risk premium, is approximately 1/2 wealth times absolute risk aversion times k squared ex squared. And we're going to define wealth times absolute risk aversion as relative risk aversion. This is the coefficient of relative risk aversion. So we see that the share of wealth you pay to get rid of a risk, a multiplicative risk, is 1/2 relative risk aversion times the variance of that multiplicative risk. So this ends the first module for Chapter 1. There is a second module as well, and I will record that separately.